It's time to discuss momentum. Like usual, we're going to start with a question. Imagine you have two objects. One of the objects has more momentum than the other. Which object is traveling at a faster speed? Try to answer this. Okay, before we answer this, we're going to go through a couple more. Now we have a large semi-truck and a small car, and they're both at rest waiting at a red light. Which vehicle has more momentum? What do you think? Last question. Consider the following two objects. We have a heavy truck parked in a parking lot, or we have a butterfly fluttering along at 1 mile per hour. Which of those two objects has more momentum? Before we can answer these questions, we need to define what momentum actually is. So let's do that now. Momentum is defined with the symbol P. Now, why P? It doesn't seem to have any connection to momentum. Well, the first problem was that M was already taken. Mass uses that. And P has a connection to the Latin, some Latin word related to momentum. So anyway, long story short, P we're going to use for momentum. And we define momentum as mass of an object multiplied by the velocity of that object. It's simpler if we write that relationship like this, where this assumes the multiplication between mass and velocity. This is an important definition. We're going to use it quite a bit, so I'm going to highlight that here. I want to point out that velocity, we know from previous discussions, that is a vector quantity, meaning it requires information about direction and magnitude. In the case of velocity, the magnitude is what we call speed. So if you take a vector and you multiply it by a quantity that's not a vector, in this case mass, what you end up getting is still a vector. So because of that, we can say that momentum is a vector, meaning it has a magnitude, and we also need to know about its direction. The magnitude of the momentum vector is what you could call mass times speed, and the direction is simply the same as the direction of the velocity. So let's imagine we have a little toy car. It's zooming along at 5 meters per second to the right. Okay, so this is its velocity. We have speed and we have direction. To find its momentum, we need its mass. So let's just say we have 2 kilograms for our toy car. Now we can define the magnitude of momentum as the mass times the speed, which gives us a magnitude of 10 kilogram meters per second. I want to highlight this unit. There's no special name for the unit of momentum. It's just kilogram meters per second. To finalize our vector property, we need to add the direction, so that would be the same as the velocity, or you could just say to the right. So now we're ready to answer those 3 questions. Let's start with the first one I asked, when I had object 1 with more mass than object 2, and we wanted to know which one is traveling at faster speed. Look at this question again and see if you change your original answer. I'm going to say for this question, D would be the correct answer. We need more information if we're going to answer this question. Let me show you an example. Okay, so here I have the momentum of object 1 as 10 kilogram meters per second, and object 2 as 9. So clearly object 1 has more momentum. But this value of 10 can be achieved by having a 10 kilogram object going 1 meter per second. 9 can be achieved by a 3 kilogram object moving 3 meters per second. So when we compare speeds, clearly the second object is going faster even though it has less momentum. So my point is that just knowing which object has more momentum doesn't really tell you what the motion is. You need more information to make use of a momentum value. The second question, we had a large semi-truck and a small car at rest. Which vehicle has more momentum? Have you changed your answer on this one? The answer is they have the same momentum. Let's consider why. First of all, at rest means you have a speed and velocity of 0. Momentum is mass times velocity. So if we have mass times 0 velocity, that means we have 0 momentum. Notice that it doesn't matter how much mass you have if you're not going anywhere. If you're at rest, you don't have any momentum. So this is an often misunderstood question, and the reason why is I think in this case people are confusing the concept of momentum with inertia. So you would say that the large semi-truck has more inertia than the small car, but those aren't the same quantities. Inertia is more related to mass, so which is obvious in this case the large semi-truck would have more mass. All right, last question. We had a heavy truck parked in a parking lot and a butterfly fluttering along at 1 mile per hour. At this point, I hope it's obvious that the butterfly would have more momentum. Similar to our previous discussion, a parked heavy truck has 0 momentum. It doesn't matter how much mass an object has, if it's not moving, there's no momentum. The butterfly is tiny in terms of mass, and it has a very low speed, so its momentum is small, but it's not 0, and therefore it's bigger than the truck, no matter what the truck weighs. Here's an example of some common objects and the momentum they have. The units of momentum are not something that we deal with very often, so it's normal to not really understand what these numbers mean. So what I do is I make a comparative evaluation. I compare the two momentums, and that makes better sense to me than the actual units themselves. So for example, a pitched baseball at 40 meters per second, it's about 80 miles per hour. So that's fairly fast. It has a momentum of 6. In comparison, a bullet, which is traveling much faster, only has 2. So the pitched baseball is 3 times more momentum. Now, if you were given the option of getting hit with a pitched baseball or a bullet, there's no question you would take the baseball. So this is an example of how just knowing momentum doesn't really describe the outcome of a situation. There's a lot of little detail that's important. Now, if you compare a car, though, on the other hand, because the car has so much mass, it's going to have a large momentum, even at relatively low speeds, although this isn't slow speed, but even at small speeds, it's going to have a lot of momentum. And in that case, it's pretty much always bad to get hit by a car. So, this is the kind of practice you have to get understanding momentum. All right, here I have a picture, some still frame pictures of a frog jumping. And I want you to answer this question: why does a frog have long legs? I'll give you a few seconds. What do you think is the answer? We're going to come back to this later. Here I have a picture of some barrels that looks like they're on some sort of exit for a freeway. I'm sure you've seen these, something like this, driving around. What are they for? Well, I realize the picture here is a little bit low quality. It was actually hard to find good pictures of these things. Apparently they're just not hot targets for pictures. Here's a different view. And maybe one more here. So if you notice, they're always stacked in front of something. I found this cool video. Nice. I was told that, or I read that the driver survived this, so I at least can be happy about that. All right, well, what these are for is they're supposed to be full of water, and they're meant as safety devices. Okay, so they're supposed to help us survive in an accident, in a collision or a crash. Okay, so let's go through the physics of why those are helpful in terms of safety. So in a collision, we know that our momentum changes. That's just going to happen. So I'm going to define change in momentum as the final momentum you ended up with minus the momentum you had right before the crash. So this is before the crash, and this is right after the crash. All right, it's simpler if we just write it like this. So the change in momentum is delta. So delta is a mathematical symbol, or we can use it as a mathematical symbol to represent change in, and it's final minus initial. If we use our definition of momentum, then we can write it like this, where the F stand for final and the I's stand for initial. So mass times velocity final minus mass initial times velocity initial. Let's look at how exactly we change momentum. Well, everything we need is right here. So this is our initial momentum quantity, this is our final momentum quantity, and there's only two options in those. So the first one is we change momentum by changing our velocity. Now, of course, that's speeding up or slowing down, but remember the velocity is a vector and direction matters. So the third way you can change velocity is to change your direction, even if you have a constant speed. So any one of those three will change your velocity, which changes your momentum. The other option is just mass. So if we change our mass, then that will change our momentum. So gain mass or lose mass, those are the only two options there. This is a good place to take a break, so I'm going to end here. If you notice, I never answered the question about why frogs have long legs, and I never explained the physics behind the water barrels. I'm going to save that for our next video.